All right. Let's see. I have this frozen. You're not going to let me forget that, are you? Okay. Somebody want to tell us on number 1, we're looking for groups of how many?
3.
3. Sounds like a bunch of people want to tell us. Groups of how many on number 2?
2.
2. On number 3?
3.
3. And number 4?
2.
2. Okay, so I'm going to show you, I did some factoring. You can write this work down or you can do this in your head. So I'm looking for groups of 3. I'm looking for a group of 3. There's a group of 3. That's going to be represented by 1, 2 on the outside. Don't forget to write the index there. If you wrote down the answer, make sure that it's a cube root, not a square root. And then there's a 2 stuck underneath because that last 2 doesn't have anything to triple it up with or put it in a group of 3. We use 16 on the cube root. Now 16 on the square root. I've got a pair of 2's here and a pair of 2's here. Or I could have thought of that as a pair of 4's. 2 2's on the outside is the same as the 4 on the outside. So we've got a 4. We've got a, square root of 3. Make that look right. Okay. So we got this one. We got this one. Group of 3. So that's on the outside. We've got a 2 times a 3. So we end up with a 6 on that one. And then the last one, we're looking for a pair. Group of 2. Take that 2 on the outside. There's already a 3 on the outside. So that's going to be a 6 and then a square root of 5. Raise your hand if you got all 4 of those right. All right, not bad. Okay. If it took a little longer than you were hoping for that to come back to you, then we maybe need to work on that just a little bit. Okay. So combining radicals is kind of like combining like terms. In order for them to be like terms, Jack, put it on my desk.
Oh, Jack. It's jacked up.
Just put it right there. That's fine. Okay. In order for radicals to be like radicals, kind of like terms, they have to have this. They have to have the same root and they have to have the same radicand. Same root, same radicand. So that means they have to have the same stuff underneath and the same index. So some examples of like radicals would be this. If I've got a square root here, I've got to have a square root there. If I've got a 2 as a radicand here, I've got to have a 2 as a radicand there. If I've got a cube root here, I've got to have a cube root there. The indices have to be the same. It's got to be the same root, and it's got to be the same radicand. Now, in order to mess that up and make a couple of non-examples, all we have to do is screw it up so it doesn't have the same index. So if I want to change this and make this a cube root, those are no longer like radicals because they don't have the same root. They don't have the same index. And if I want to mess this one up, let's say I want to keep the index the same, all I have to do is change the radicand and get something else. So say I have a 4 right here, then that would be a non-example. Those things are not like radicals because they don't have the same root and the same radicand. Everybody good with that? All right, now in general, okay, it's usually best to simplify before combining, and then we always want to make sure we simplify our final answer. So on a problem like this, same root, same radicand. So if I have minus 10 of those, plus 12 of those, I have 2 of those. I don't get something different. This doesn't turn into a 14 or something weird like that. I'm literally counting up how many of those I have. So this is going to be the 5 square root of 3, 2 square root of 75. Doesn't look like they're like radicals right now, but again, we haven't simplified this, so let's check and see what we get. This is going to be a 25 times 3, 5 times 5 times 3. So I've got a 5 radical 3. If I pull that 5 on the outside, this is now a 10 radical 3. So I end up with 15 radical 3. Everybody good there? They're all square roots, so they all have the same root, but none of them have the same radicand, or at least it appears that they don't for right now. So let's check and see. Pair of 2's on the inside. 10 radical 2 when we simplify that one. And again, I'm writing down the arithmetic or the factoring that you might be able to keep in your head. Pair of 3's. So that's going to be minus 9 radical 2 there. And then plus radical 3. So the only thing that are like terms are, even though they're all square roots, these have the same root and the same radicand. So we end up with radical 2 plus radical 3. Simplify, and that's our answer. Now, if this were a calculator portion of a test, you could make yourself feel a little bit better that you got the right answer. You could literally type in the original problem, hit enter, type in your answer, hit enter. It would probably give you ugly decimals for both of them, but as long as they were the same decimal, you would know that you got the right answer. Everybody good there? Okay, any questions? Okay, I have a talk with some of my classes about making sure they ask honest questions and then they're honest with themselves about what they need. That's what class is for, to help you get what you need. So if you need something, make sure you ask. This is a cube root of 40. We're looking for triples, groups of 3. This is 8 times 5. That's a 2, a 2, a 2, and a 5. Group of 3, one of those 2's on the outside. 5 left underneath. Nothing to simplify there. 3 cube root of 5. We got a cube root of 135. Okay, I'm thinking that that's a typo. That's what I'm thinking. Okay, I'm thinking when we changed this, we didn't quite grab that. So would you change that to 2 and somebody, no, should we leave it that way? No, let's leave it that way. Because let's see, 135.
15.
15 goes in how many times? 9 times. I'm okay with that. Okay, so this is going to be 15 times 9, which is, wait a second, does this work? 3 and 5 and 3 and 3. So even though it looked kind of nasty, gosh, if it were a cube root of 125, that would be cool because it turns out to be a nice number and everything. This actually works, doesn't it? Because you've got, even though they're not together there, we've got a triple. We've got a group of 3 3s. So this is going to be plus 6. Cube root of what's stuck underneath? 5. Caleb, can you tell us why that 5 stuck underneath? Yeah, it's not part of a group of 3. It's not part of a triple. So all together here, if I put the 2 of those together, I don't know if your brain works this way, but mine does if I'm doing arithmetic. I'd rather put the positives together. I get 8 of them. Then I subtract 3 of them. And then we end up with 5 cube root of 5. Anybody brave enough to say they wrote 5 square root of 5? They didn't put the index in there? Oh, I hope that's nobody. Okay, take a look at the next one. Would you apply the same ideas there? You may have seen something like this before, but maybe not. Andy, groups of how many? Groups of 3. That's an 8 times a 3. If I really belabor the point, triple of x's, triple of 2's. So this is 4x cube root of 3 minus x cube root of 3. And for some people, this does get a little bit weird. Everybody know what the answer is? Mason's got his hand up. Zach's got his hand up. Colson, right?
Yeah.
Andy? 4 cube root of 3? Because we're subtracting the x's, so I've got this x minus that. Okay, so 4 cube root of 3. Anybody else want to differ with that? Mason?
Well, I don't know whether you treat the x as like a coefficient to the 4, so it'd be like 4x minus x.
Okay.
And then you'd be 3x cubed root of 3.
So what do you think the final answer is?
Oh,
You're raising some good points. What do you think the final answer is?
I bet it'd be 3x.
3x cube root 3? Dane?
I would just do 3 cube root of 3.
3 cube root of 3. Just plain old 3 cube root of 3. Okay, we got a bunch of stuff floating around here. Okay? All right. How about this? Okay, I want you to listen to this carefully. Remember, we talked about radicals can be written with rational exponents, right? Okay, so here is what I think of as the ultimate rule for combining like terms. Like terms have things that have the same base and same exponent. Same base, same exponent. Doesn't matter if the base is a variable or a number, has the same base and same exponent. So I want to ignore this for the time being. Ignore the radical part for the time being. Okay, if you look at the variables and you think of the variable as a base, so just pretend like you can't see that. I know you can. The base is x. What's the exponent? 1. So this is 4x to the first minus 1x to the first. That would be 3x's, right? The answer would be 3x. Now, if we extend that to this guy right here, the base would be 3. What would the exponent be? What is it? We did it last week. It's been 3 days since we did it. To the 1/3. This is 3 to the 1/3, and this is also 3 to the 1/3. So they have the same base and they have the same exponent. These have the same base and the same exponent. So that means the variable part of each one of these is exactly the same. The like term part of this and the radical part is the same. So the stuff that I just highlighted in yellow is how many things we're counting. We have 4 of these things minus 1 of these things. So how many of those things do we have?
3.
We have 3 of those things, not 3 of something else. So this is 3x cube root of 3. Raise your hand and be honest. Did you get that right? Raise your hand if you got that. Ooh, not too bad. Not too bad. Okay, not quite half, but that's pretty good. Any questions? Yeah.
Well, I was just gonna say, couldn't you just think of it as whatever you have to take out, you multiply by each other? So in order to and if you didn't group them together, then you would have to divide to get the x's to go away or something.
I kind of see what you're talking about, but yeah, I think, does it produce the right answer? We just want to try that out in a couple different situations. Okay, take a look at this one right here. These are just numbers. I'm hoping this is pretty easy. I'm going to give you a 10-second head start. This is one reason why I like teaching you guys. Most of you keep your head down because you want to figure out how to solve it yourself. This is what I did. Did I show enough work to be really convincing that I know what I'm doing? And did I get it right? Colson, is that what you got?
Yeah.
Okay. What was I doing up here? Showing the factors, showing how many groups there are and stuff like that. So even if somebody came by and looked at my work and didn't listen to the explanation while I was doing it, they'd kind of see what was going on there. Any questions? Raise your hand if you got that one right. That makes us feel better. Okay. Multiplying radicals is pretty easy, especially if they have the same index. Okay, we just multiply the coefficients and multiply the, let's see. They've got the same index. We'd multiply the radicands. So what we're basically doing is we're using the product property of radicals. So the product property of radicals was this. You can find the radical of the first piece and the radical of the second piece separately, but we're using this in reverse because remember, these can be used in both directions. So what we're doing here is we're kind of using this backwards. If we're multiplying them and they have the same root, the same index, we can just put them underneath the same radical and then multiply those together. Now, you're going to want to be aware of something when we do this, so watch closely. Okay, so in general, so we're going to review this. A product is a multiplication problem, or the answer to a multiplication problem itself. And in general, it's usually best to leave the radicand in factored form until you're done simplifying the radical. So don't bother multiplying these together because we're going to get a gigantic number anyway. So let me show you what that looks like. On this problem right here, if we're multiplying these together, we're just going to multiply the coefficients together. So we're going to get a 6 on the outside. Then when I multiply the 6 and the 7 that were underneath the radicand together, I'm not going to bother writing 6 times 7 because if I multiply those together, I end up with a 42. And that right there is the answer. Now, the reason why this is a super simple problem is, even if I were to factor this out, this is a 2 and a 3, and this is a 7. Caleb, we're looking for groups of how many? Groups of 2. I got a 2, a 3, and a 7. I don't have any groups of 2, so I just multiply them all together. I get a 42. We might as well just think of 6 times 7 as 42. But this problem is very different. We're not going to multiply those together and get 400. And we're not going to multiply them and get to x to the third. I suppose we could if we wanted to. I'm going to have a 4 on the outside, and we're going to have a cube root. Notice it is a cube root. That's the index. Those are the same. 20 times 20 times x times x times x. If you wanted to, you could write it as x to the third. But immediately we notice that we've got a group of 3 x's. So we know we're going to have an x on the outside. Rather than write 20 times 20 on this particular problem, because we're looking for groups of 3, it would have been smarter for me to start writing out what instead of 20 times 20. Yeah.
400.
We could write 400 if you want to. I'm thinking of something different. I really don't want to make the numbers bigger. Yeah.
2 times 2.
There we go. So instead of writing it this way, I probably would have been better off thinking of it this way. This is a 2 times a 2 times a 5 times a 2 times a 2 times a 5 times an x times an x times an x. And again, if you want to write the x times x times x, if you want to write that as x cubed, that's totally fine. But we're looking for groups of factors anyway, so everybody stop, look up here. Why do we want to make the numbers bigger when we're going to factor it in our heads or on paper anyway? So why would we want to multiply it together and get 400 if you're just going to have to break it down into factors anyway? Because 20 is really easy to break down, and we just write it twice on this particular problem. So I'm looking for groups of 3. There's a group of 3. Any other groups of 3? Just the x. So on the outside, we're going to have another 2. That's going to make an 8. We're going to have an x, and then a cube root of, it's a pretty big number, but still there's nothing there. So this is going to be a 50 underneath there. 50 is made up of a 5, and a 2, which you would think you'd be able to take something out. If this was a square root, you could, because that would be pairs of factors, but this is a cube root, so we're looking for groups of 3. Everybody good there? Okay. Okay, I didn't say anything, did I? Can you tell what I was thinking? What was I thinking here? Zach?
There are 3 2's, so
Yeah.
it become
Yeah, so why write it as an 8? Although it's a small enough number, you could have written it as 8. We're kind of demonstrating a principle. Why did I write this one as a number rather than factored form? Keely? Yeah, we got 2 2's and we got a 5. Nothing there. So this is going to be a 2 minus cube root of 20. Any questions there? Okay, flip the page over. Get some interesting problems. Raise your hand if you've seen problems like this before. A couple of you. Okay. All right, take a look. It's kind of like multiplying binomials, which you learned how to do last year. radical 6 times radical 3. I'm going to write, or I'm at least going to think that. I did radical 3 times radical 6. There's the 3 times the 6, but I'm going to write it in factored form. I've got a coefficient of -3, and I've got a radical part of radical 3. Then I've got plus 2 radical 6. I really don't need to worry about that one because radical 6 doesn't simplify. And then I've got a -6. Clean anything up I can clean up. Pair of 3's. 3 radical 2. And then I look at the rest of it. What am I looking for in the rest of these if I'm going to simplify this? What am I looking for? Same root, same radicand. I've got a bunch of them with the same root. None of them have the same radicand. So guess what? We get this big, gigantic, ugly mess for an answer. And why aren't those 6's like terms? Because one of them's not a 6, right? You put radical 6 into the calculator, you get big, long, ugly, irrational number. This one's a little bit of a different story. Do that part first. Mason, will you grab that door when you get a chance? This will happen a lot when we're multiplying binomials with radicals. We end up with a -6 from this one because there's a pair of 3's we can take out. These are like terms right here, so I end up with 12 of those all together. And if I wanted to take the time to write all of this out, I'd do that. And then I normally write the non-radical term first, and then the radical term second. It's not a huge deal what the order is like there is with variables and stuff like that. Okay, did I do okay? Raise your hand if you got that. Okay, any questions? Okay. Who's done with this one? Good, go. See what happens. It's kind of unique. I'm hoping to hear some what'd you get? This is what I got. How did you get that? Oh, that's interesting. Gavin, would you be willing to tell us what you got?
Sure.
What'd you get?
41.
You got 41. Raise your hand if you got 41. All right. If you didn't get 41, no problem. You may not have seen a problem like this before. Kind of cool when the radicals cancel each other out. So we just get a constant, a nice whole number here. And then we get a nice integer at the end. And these two happen to cancel each other out. One of them is -15 radical 2, and the other one's 15 radical 2. So we're all good there. Any questions? Okay. Even if they do have the same radicand, if we're dividing radicals, it can still be a little bit more difficult than either combining or dividing. The coefficient part is still pretty easy to take care of. We kind of do that like we do fractions, but we do have to be careful when we're doing this and simplifying. We're going to use the quotient property of radicals. So here's the deal with that. If you have the radical of a quotient, or in other words, we've got a fraction underneath the radical, You can find the radical of the top and put it over the radical of the bottom. And again, just to emphasize this, because these are not the only ones that work in both directions. Tons of mathematical properties like this do, so don't forget you can go both ways on this. So a couple of these rules are this. We can't leave a fraction underneath the radical, and we can't leave a radical in the denominator. So we're going to end up rationalizing a bunch of these. But if we get lucky, absolute piece of cake. 4 on the top, 9 on the bottom, done. Doesn't really get any easier than that. Couple different ways to do this one. Okay, I'm going to show you the way we do it using the property, and then I'm going to show you the way I like doing it. So here's how you use the property. Okay, I'm not quite done. Yeah.
For A, wouldn't it be 4, 6?
Oh, 4, 6. Oh, thank you for telling me. Okay. Yeah, grab me sooner if I make a mistake like that. Okay, 4, 6, and then what do we get? 2/3. Thanks. Excellent. Okay. All right, now we're back on track. Thanks for catching me there. Sometimes I get distracted. Okay, I'm not done with this, but let me show you the way I would rather do this one. I'm going to change colors. This is a radical 3 on the top. There's nothing you can do about that, but I'm going to take advantage of the product property of radicals, and I'm going to think of this as 2 times 3. So this is radical 2 times radical 3. So I get 1 over radical 2 either way. I'm not done with this, but does everybody see the 2 different ways to simplify that? They both work perfectly well. Kind of personal preference there. Okay, I'm going to change to green, 1 over radical 2. Does anybody remember how we rationalized the denominator? How do I change that to a plain old nice number? Fractions are hard enough without having radicals in the denominator. Samara?
You multiply by the radical of 2.
Yep. And does anybody remember why we do that? Lizzie?
Basically just multiplying it by 1.
You're multiplying it by a funny looking 1. I'll take that. And how many 2's do we need underneath there? 2. So we're giving it enough to make a pair or a triple or whatever it happens to be. Can I cancel these? Can I cancel that 2 with that 2? No, because when it's underneath the radical, it is not a 2. It's a really ugly number. It's about 1.414 or something like that. So let's take a look at the next one. This one, it doesn't really matter which way you do it. I'm going to take care of the numbers in front, so I'm going to have a 3 on the top. And whether I write it like this or whether I do this, either way, when I cancel these off, what I'm going to have is I'm going to have a radical 10, and that's on the top. The numerator completely cancels. Okay. If you want to think of it as just canceling like that, you can, although you do want to be a little bit careful with that. Everybody good? Okay. Any questions so far? Okay. Let's take a look at these guys. I got a 22 and a 44. I kind of like that because I can just make that a 2. I've got 3 x's on the top and I've got 2 of them on the bottom. So those 2 will cancel with 2 of the ones on the top. That'll leave 1 x on the top. So I have an x over a radical 7. Okay? Luke, I can't leave a radical in the denominator. I've got 1 7 right now. How many more 7s do I need in order to take them out? 1 more. So I'm going to give it the number that it needs. So I'm going to multiply the bottom by radical 7. I can change a fraction into another equivalent fraction as long as I multiply the top and bottom by the same thing. So if I multiply the top and bottom by radical 7, I'm going to end up with this. X radical 7 over 7. And we normally do write it like that. This is a case where we don't write the x at the end. Yeah.
What about the 2?
Oh, the 2. So is there a 14 there? Okay, thanks. Good catch. I should put that out here. Okay. This is a case where we don't write the x at the end. We write it at the beginning. Anybody know why we don't write it on the end? somebody might confuse it for being underneath with the radical. They might not know how long that bar is with the radical. Okay? Would you simplify e, please? Do e on your own. Dane, why are you smiling?
Easy.
Because it was easy. What made it easy? Here's how I did it. What'd you do?
Oh, I just did it so it was the square root of 9 over 1, so it's just the square root of 9.
Okay. You just simplified there. Square root of 9 ends up being 3. Both are perfectly good, right? Okay. All right. Last one. Would you do that one? And if you think you've got the last one, then think about the thought questions at the bottom. Let's see. What's your name again?
Crew.
Crew, that's right. I was thinking Cash, but that's way off. Crew with a K?
Yeah.
All right. I got to keep that in mind. Crew, how am I doing on F?
Yeah, it looks right. You just have to get the radical on the top.
You just have to get to the radical on the top. And how do you do that?
You times it by like the radical 10 and over 10.
Because I need another 10, right? I got a 2 and a 5. I need another 2 and I need another 5. So I get a radical 10 over a 3 radical. Wait a minute. Radical 10, radical 10. What does that put on the bottom then? That puts a 30 there. Okay. Is that right? Raise your hand if you got that. Okay. Did anybody notice any special relationship between those two problems right there? Luke?
So I decided that I was lazy and I wasn't going to do the math, so I just took the reciprocal of what we got
Yep.
on C.
Yep, because they were reciprocals of each other.
And then I removed the radical from the
You did
bottom.
this stuff right here. So what you did is you jumped from there to here. You noticed that they were reciprocals, so this should be the answer. But there it's in the right form. Here it's not, so you've got to rationalize the denominator. Is that fair to say?
Yeah.
Okay. Everybody good? Okay. That's it for the stuff that you're going to see on your assignment. But if you take a look at these guys right here, how would you deal with those problems? I think we've seen one like A. We have not seen one like B before. So stop and think about each one of those. Okay? Just look, I'm going to pass out the assignment. And before I call on somebody, and I've got a bag of high chews over there. You can probably have a couple if you answer one of these. A's the easy one, so I'll give away 2 for that one. Or if you don't like high chew, we can find something else. D.
Cube root of 2 plus 2 square root of 2.
Are we adding?
Multiply.
We're multiplying. Okay, so cube root of 2 times 2 square root of 2. That the end answer? Lizzie?
Could you change the radicals into exponents?
What would the exponent on this one be?
It would be a 1/3.
This would be a 1/3.
And then 8 would be 1/2.
8 would be a 1/2.
And then simplify it or multiply
Let's see. We can, but what do we have to do with these guys right here? Do they have the same base? They don't. So we'd have to do something like this. This is 2 to the 1/3, and this is 2 to the 3rd to the 1/2. Sorry. Yeah, that's right. Is that okay? Is that where you were headed?
I think so. I think I multiplied it wrong.
Okay. Does everybody agree that the cube root of 2 is 2 to the 1/3? Does everybody agree that this is 8 to the 1/2 power? Everybody agree 8 is the same as 2 cubed? Power to a power, what would we do with these? Multiply them, so this would be 2 to the 3/2. Same base, we're going to multiply these together. If this was x squared times x to the 3rd, everybody in here would know what to do. But you look at something like this and it gets a little confusing. So a good mathematical tool, I think I mentioned this last week, is come up with a simpler example where you know what to do. This is x squared times x to the 3rd. You would do what with the exponents? Add them together. What do you do here? Add them together. What's the common denominator? 6. So we're talking about 6th roots here. So this is going to be, let's see, that would be 2 6, and that would be, how many 6? 9 6. So we've got 11 6. 2 to the 11 6. Is that how you'd write the answer, though? Yeah. Yeah, so this is going to be the 6th root of 2 to the 11th. Okay, I want you to stare at that for just a second. Notice that we didn't simplify it. That's a very interesting problem. If you can navigate your way through those bases and those exponents, that's awesome. We're not done with that one. I want you to take a look at the next one. I'm going to ask somebody in here groups of how many, and somebody's going to tell us. Then I'm going to ask how many do we have, and then I'm going to ask how many we need. So Andy, groups of how many on problem B?
3.
Groups of 3. Okay. Let's see. Megan, how many do we have down here? How many 2s do we have? We have 1. How many did you say we needed?
3.
We need 3. So I've got 1 2. I need 3 2s. So the question here is, what do you multiply by to rationalize the denominator? You don't have any of like this on your assignment. We're going to come back and we're going to look at this one and we're going to look at this one first thing tomorrow. If you want to think about them, your assignment's on that paper. There's a front side and a back side. There are 33 problems altogether. Size seems pretty reasonable about how many we should get rid of. Should we get rid of any?
Yes. I say
Multiples
multiples of 3.
of 3. Oh, see, the last time, I put my trust in him. Let's get rid of.
5. Yeah, I think 5.
You got some input? Oh, you figured out how to do it. Isn't that nice? Wait a minute. Are you experiencing satisfaction due to math?
Okay, once. This
Once.
is once.
Okay.
That's different.
Get rid of multiples of 5. Get rid of multiples of 5. You're
you.
welcome.
Thank
In exchange for getting rid of multiples of 5, I want you to think about these. See if you can come up with an answer for the both of those.
We'll just say satisfaction is a rarity.
Okay. Which one?
Multiples of 1/2.
Because I just got it to that. So now
Okay. All right.
Exactly.
I should go
I
up
love
that.
multiples. You got rid of multiples of 1 excluding 3. That's 2. Well, I got homework.
Oh my gosh, Dave, what did you do?
Wait. Oh, my brains.
So what you're saying is that you got the utter disdain for Dane?
What are we on?
Could that possibly be?
Disdain?
Yes.
Or did I? No. Wait.
There we go.
No, that thing. Oh,
Oh, okay. So you have to. Oh, okay. Wait. No, dang it. Now I want to hurry and figure this out. I have language arts next.
What's that?
Is the answer to the problem like 6 root of 5 over